A coil is connected to a 60 Hz 120 volts AC generator. At this frequency, the coil has an impedance of 10 ohms and a reactance of 8 ohms. Let's write down what the problem gives us. The problem gives us the frequency of the generator, 60 Hz, and the maximum voltage across it, 120 volts. The entire circuit is made up of a coil that has a certain impedance and reactance. That means we can write the impedance of the circuit Z as being equal to the impedance of the coil, equals 10 ohms, and the reactance is 8 ohms. Well, this is a coil. The reactance is the inductive reactance, XL, equals 8 ohms. In part A of the problem, we need to find the current in the coil. We are given the maximum voltage and we are given the impedance of the circuit. Therefore, we can find the current simply by dividing the maximum value of the voltage across the circuit to the impedance of the circuit. V has a value of 120 volts and the impedance is 10 ohms. Therefore, the current in the coil, the maximum value of the current in the coil is 12 amps. In part B of the problem, we need to find the phase angle between the current and the applied voltage. Well, in that case, we can use the equation that gives us the phase angle. Tangent phi equals XL minus XC divided by the resistance R. We do not have a capacitor in this circuit, therefore XC is 0. We do have XL, the inductive reactance of the circuit, 8 ohms, but we do not have the resistance. We do know though that the impedance is related to the resistance, inductive reactance, capacitive reactance through this equation. Z equals square root of R squared plus XL minus XC squared. Remember once again, XC is 0. So what I have left under the square root is resistance squared plus XL squared. We know Z, the impedance, we know XL, we can find the resistance. We square this equation and we have impedance squared equals resistance squared plus reactance squared. And we replace the impedance with 10 ohms and the reactance with 8 ohms. And from this equation we obtain that the resistance of the coil is 6 ohms. Now that we know the resistance, we can go back in the equation for the tangent of the angle phi. And we replace the reactance with 8 ohms and the resistance with 6 ohms. And we get that tangent phi, the tangent of the phase angle between the current and the applied voltage, is 8 over 6. Using inverse tangent, and don't forget to put your calculator in radians, we obtain that the phase angle between the current and the voltage is 0.92 radians. In part C of the problem, we need to find the series capacitance required so that the current and voltage are in phase. When the current and voltage are in phase, the capacitive reactance and the inductive reactance are equal to each other. Since we know the inductive reactance and we know that the capacitive reactance can be written as 1 over angular frequency omega multiplied by the capacitance, we can find the capacitance from this equation as 1 over the angular frequency omega multiplied by the inductive reactance, XL. Don't forget that the angular frequency is related to the frequency of oscillation of the current in the circuit. Omega is nothing else than 2 pi times the frequency. And all we have left now is to replace the numbers given to us. The capacitance is equal to 1 over 2 pi. The frequency F is 60 Hz. And the reactance for the inductor is 8 ohms. And we obtain a value of 331.7 times 10 to minus 6 farads for the capacitance that is required to be connected in series with this coil such that the current and voltage are in phase. In part D of the problem, we need to find the voltage measured across the capacitor at resonance. the maximum voltage measured across the capacitor is calculated as the current times the capacitive reactance of the capacitor. We need to find the current at resonance. Well, the current at resonance will be equal to the voltage, maximum voltage V, divided by the impedance at resonance. Well, the impedance at resonance is nothing else than the resistance of the circuit, because XL equals XC, and they cancel out in the definition of impedance. So the maximum value of the current at resonance is the maximum voltage divided by the resistance R. We replace the current in the equation for the voltage across the capacitor, and we have that the voltage across the capacitor equals the maximum voltage V divided by resistance, multiplied by the capacitive reactance. We know all these values, and we replace the maximum voltage with 120 volts, the resistance with 6 ohms, and the capacitive reactance with 8 ohms, which is the value for the inductive reactance. Don't forget, at resonance, the capacitive reactance XC equals the inductive reactance XL. So both of them have the same value of 8 ohms. And we obtain a value of 160 volts for the voltage measured across the capacitor at resonance.